Well, hello. We're having a look at today in the area of dynamics at resolution of forces and also the very interesting area of inclined planes. So let's get going and have a good time together. Now, in this example here, it's a very simple example. We've got a particle at the origin acted on by forces of magnitude 3 newtons and 5 newtons respectively. The resultant force was determined in a previous example, and we'll give you that information shortly. If the particle has mass of 1 kilogram, we now have to find the acceleration, and we have to state the direction of the acceleration. Well, guys, if we know the direction and magnitude of the force, and we also know the mass of the thing, then according to Newton's law, we can use F equals ma, can't we? To find the acceleration, and the direction of the acceleration will just be in the direction of the force. Well, I think I've just about told you the whole thing. So, here we go. What do we got here? Apparently this is what we got in example 1, I can't remember. So it was a force of 7.43 newtons, and it must have been at an angle to the positive direction of the x-axis of 31.59 degrees. Okay, now, from example 1, so there we go, that's what I was saying, F equals ma, and if you sub F equals 7.43 and m equals 1 kilogram into F equals ma, you're going to get that. Okay, so therefore the magnitude of the acceleration will be 7.43 meters per second, and the direction will be 31.59 degrees anti-clockwise from the positive direction of the x-axis, is what I'd rather say there rather than just the horizontal. Okay, that's very simple, very simple, just to illustrate the F equals ma concept. Let's keep going to another one. Okay, a block of mass 10 kilograms is pulled along a horizontal plane by a force of 10 newtons, inclined at 30 degrees to the plane, that is, the force is inclined at 30 degrees to the plane. The coefficient of friction between the block and the plane is 0.05. So we've got some friction now, guys. Find the acceleration of the block. Well, I think that's pretty easy, but we better do a diagram first, because a picture's worth 1,000 words after all. Don't you know? You do. Okay, so what do we got here? This looks like my mass, and there's 10g, the force downwards towards the centre of the Earth, and we've got the normal force, which is always perpendicular to the plane. That's the reaction force of the plane on the particle as a result of it pushing down through the plane with a force of 10g. Now, what we've got here, guys, is our 10 Newton force. Okay, that's an external force pulling it along, and the external force is 30 degrees to the horizontal, as you can see here. As a result of that force, we have a resistive motion, resistive force here, which is the frictional force, which, if the body is on the point of sliding or already sliding, which it is in this case already sliding, then you have the limiting friction force. We'll go into that into more detail later on in this series on dynamics. But the limiting friction force is related to the normal force, and it's mu, which is the coefficient of friction, times the normal force. Okay, you get that? And we're told that the coefficient of friction is 0.05. That number varies according to the roughness of the plane, and therefore the scratchiness with which it has to overcome when it's being pulled along the plane. Okay. So a scratchy plane, a rough plane, would have a higher coefficient of friction than a smoother one. Okay, infinitely smooth with no friction, mu would be 0. Okay, now this here, guys, is saying that the sum of all the vertical forces, note the tilde saying it's a vector, the sum of all the vertical forces would be 0, because there's no net vertical force, because the body's not levitating off the plane. See, no net force, no net movement. That's what that means. So therefore, we can say that therefore 10, now this is the up. The up equals the down, okay? That's how I do it. I don't bother about with the I and J notation with these things. I just go up equals down. So the 10 sine 30 is the vertical resolute of this 10 Newton force. That's in the vertical direction. Okay, you'd have 10 cos 30 along here, 10 sine 30 going up there. So 10 sine 30 plus n, they're the ups, equals 10G, which is the down, okay? Because they're exactly balanced. There's no net force, no net movement, no net anything, okay? So therefore, there we go. 5 plus N equals 10G, therefore N will be, that's what we're trying to find here, guys. 10G minus 5. Now, G is 9.8 in Melbourne, Victoria, Australia. And it'll be very close to 9.8 wherever you are. It just varies a bit according to the elevation. In other words, how far you are away from the centre of the Earth. On Mount Everest, it would be a lot less because you're significantly further away from the centre of the Earth. It wouldn't be a great deal less, but it would be less. Okay, so what do we got? 98.5, which looks like 93. 93 newtons is the normal force there, guys. 93 newtons. Now, we're going to use that information in our horizontal force balance to say that the sum of all the horizontal forces does not equal naught because it's accelerating along the plane. That's right. So therefore, the sum of the horizontal forces, the net force, will equal ma. Okay, ma. So there. Now we're going to put that into action and say that therefore 10 cos 30, which is this little one here I was explaining before, 10 cos 30 is the horizontal resolute of that 10 Newton force, minus the mu n, because this one's bigger than that one, okay? So right minus left equals ma. That's the way I'm doing it, okay? Bigger minus littler equals 10a. And mu, we know what these species are now, don't we? We do. So, therefore, we're going to work out a, which is what we're required to do. There we go, guys. Look, we're getting very close to victory now. So just simplifying that a bit more, we've got 5 root 3 minus, now, that looks like that'd be right, wouldn't it? Because that'd be 5 times 93 over 100, which looks pretty right. Yes. 4.65, and therefore we will work that out as a decimal, I think. Yes, very good. Therefore, it looks like A is 0.401 metres per second. Okay, and that's the answer. That's what we were required to work out. So, a jolly good show, and congratulations to you if you followed along with that and you understood it. Okay, well, we're hot to trot. Let's do another one. Now, what do we got here? Yes. Now, what I wanted to explain to you that in this video we are going to consider normal reaction forces and inclined planes. Now it just so happens, ladies and gentlemen, that the normal reaction force, as you see it here, this is an inclined plane scenario, the normal reaction force is always perpendicular or at right angles to the plane. This body pushes down towards the centre of the Earth on that inclined plane, okay? But you can resolve that gravitational force as part this away into the plane at right angles to the plane and part this away down the plane parallel to the plane, you see? So it always pushes on the plane so that the normal force is always at right angles, perpendicular to the plane. Some students don't understand that. It's very important that you understand that. So now, having said that, the normal force is always at right angles to the plane, and we are concerned in these inclined plane problems with motion along the plane or parallel to the plane, which means either up or down the plane. So you can kind of see that the forces that we're interested in here are mostly concerned with parallel directions to the plane and also the normal forces perpendicular to the plane, so that overall the majority of the forces that we're looking at here, with the exception of this mg, are either parallel or perpendicular to the plane. So having said that, and this is easy to resolve, very easy to resolve in terms of a perpendicular and a parallel to the plane anyway, that one force is. So therefore it becomes convenient to resolve the forces in these inclined plane scenarios parallel and perpendicular to the plane, okay, rather than horizontally or vertically. So you'll see here, my little legend here, my little legend for you to follow is that this is parallel to the plane and perpendicular to the plane. They're the directions I'm going to use for working out these inclined plane situations. It's just more convenient and it's very easy, okay? So that's what this screen is trying to say. Yes, Mr. Box, thank you. It deserves a box, this one. Now, let's, armed with that new resolution, we're going to do a couple of these questions now where we will just put that into action. First thing I want to say is I don't like this I and this J business here. That confuses me, so I'm going to ignore that. Because I to me is refers to the horizontal and J to me refers to the vertical, so I'm not doing that. I think it's very confusing, so can you just please ignore that? Now, a particle of mass 5 kilograms lies on a plane inclined at 30 degrees to the horizontal. There is a force of 15 newtons acting up the plane which resists the motion. Okay. Find the acceleration of the particle down the incline and find the reaction force R. Here it is here. They're calling it R. I usually call it N for normal, but R will do in this situation. Alright, now we're going to do exactly what we said, guys. First of all, I resolve this gravitational force into parallel and perpendicular components, or resolutes, right? Parallel and perpendicular to the plane. Now, I always do them as little dotted lines because I don't want to create the impression that I'm creating new forces. So I do this as a dotted line. This is the force, this 5G. That is the force, the gravitational force. This is just a resolved component of it, perpendicular. I also put that in brackets very conscientiously, just so that no examiner looking over my shoulder, looking at my work, is going to get the impression that I'm trying to imply that I'm inventing a new force here. You've got to be very careful with your notation. So, by the way, this little angle in here, where my little froggy finger is, that's always the same as this angle out here. You can easily prove that with geometry. It's really easy to prove. So that'll be a 30-degree angle. Therefore, this force here will be 5G cos 30. This force here will be 5G sine 30 if you just want to do the basic trigonometry in the little triangle that I've formed by using those dotted lines with a right angle here. Okay, that's the very first thing you always do. That's very routine. Now, we're going to do our force balance now. So let's balance the forces perpendicular to the plane. You notice I don't use J. I'm not using J. It's too confusing. So the sum of the net force perpendicular to the plane, note the tilde because force is a vector, is 0 because it's not moving this way. At least we don't think it is, not on planet Earth. Anyway, it might do it on planet Krypton, but not on planet Earth. So therefore, we're saying that R equals 5G cos 30, right? And cos 30, you know what that is, don't you? Please tell me you do. It's root 3 over 2, so therefore that's what R is. Now, we've got R sorted out. So therefore I think that's all we need there. There's no friction in this situation, is there? Can you see any friction? I can't. So therefore that's not going to that's going to be the end of the line there. They're asking us for the reaction force, so we found it, okay, and that's it. It doesn't get used anymore. So therefore, the second bit of the scenario here is we're going to do the force balance parallel to the plane. So the sum of the horizontal forces in this case not equals 0, it equals ma, because the particle is going to move down the plane, because that's what they told us, didn't they? Find the acceleration of the particle down the incline. Yes, so it's moving down the incline. It's only resisted by this force, not stopped by it, okay? And there's no friction to worry about either, so don't put any mu n's in there. That would be wrong. Now, not that we would be able to anyway, because they don't even tell us what mu is, because it's not a consideration. So therefore, what are we saying now? I'm saying it's moving down the plane, so this is the bigger force. This one here is the bigger force. So right minus left equals ma, right? That's because it's moving towards oh, no, wait a minute, left minus right, good heavens above. So this one is left minus right equals ma down this way. That's what I'm trying to say, yeah? Okay, getting a bit dyslexic there, sorry about that. Now, so therefore 5G sine 30 is a half, minus 15 equals 5a. We can easily work out a, and we're a moment away from a, guys. There it is. So it looks like g over 2 minus 3, which is 4.9 minus 3, which would be 1.9 metres per second down the plane. Okay, how's that? You get it? It's really easy, this stuff, you know. It's rather fun and easy marks too, which is always a good thing. Now, this one's a very interesting question. This is a sort of a compound question because we're shooting a thing up the plane. Here we're going boom, and then we're letting go. As soon as it starts its journey, we're letting go, so there's no ongoing force. pushing it up the plane, and we're just going to let it sort of come to a stop, and then it's going to come down the plane again, like that. So here we go. A slope is inclined at an angle theta, there's theta, dear little theta, to the horizontal where tan theta is 4 over 3. So I've written the geometry. See, look, 4 over 3, which means that must be 5. And that will enable us to work out sine theta and cos theta, see later on. I'm devilishly cunning, aren't I? So a particle is projected from the foot of the slope up a line of greatest slope, which just means aka according to this diagram, with a speed of v, capital V, metres per second, guys, and comes instantaneously to rest after travelling 6 metres. Okie dokie. And there's friction. There's a fraction of friction. The coefficient of friction between the particle and the slope is a half. Alright, okay, I get this. This is going to be interesting. It's all unfolding in my mind's eye. So calculate the value of V. Alright, so in other words, we better draw a force thingy, guys. I think we better do that, because otherwise we'll never understand what's going on here. Now, that looks rather nice. Now, and I've added that in the up situation, up the plane, I'm going to consider that up the plane is positive direction of motion. Mu's a half, yes, mu's a half. Here's the motion's going that way, and it's positive in that direction in my frame of reference, and I've got the frictional force mu n, and I've got the mg sine theta, the parallel component of gravity, parallel to the plane and down the plane. They are the two forces resisting the motion, all right? They are the two forces resisting the motion. There's two of them. So, therefore, we better start doing some force balances here, guys, I think. Oh, yes, okay, thank you, Mr. Computer. Sine theta is 4/5. Have a look. That's right. Cos theta is 3/5. Very good. Yes, from the triangle opposite, yes. We need to calculate the net force. Yes, of course, the net force first, and then from that, F equals ma up the plane, and then we can work out what the initial thingy was, the initial velocity was. Once we know the acceleration, we can use our license to drive formulas, our constant acceleration formulas, to work out what the starting velocity was. And I can see in my mind's eye, it's going to be v squared equals u squared plus 2ax. Of course it is. Aha, I'm getting well ahead of myself here. So, right, let's do it. Here's the sum of the forces perpendicular to the plane will be 0 because it's not going to levitate off the plane in the perpendicular direction. So, there we go. So, therefore, what are we saying? We're saying that mg cos theta, the down, equals the up. Okay? The down equals the up. All right? Very good. Now, let's go with this. That is, n equals, okay, now how did I get that? Of course I got that. Cos theta was 3/5, wasn't it? Ah, very nice. Very nice. So therefore, now, doing the other one now, we've got the forces parallel to the plane. That will equal ma. It won't equal naught. It will equal ma. Okay, now, this is where our direction, our positive direction comes in handy. Being up the plane, so the two forces will be negative, you see. So we've got minus mg sine theta minus mu n. They're both resisting the motion, equals ma, okay? And a is going to be revealed to us very, very soon. There it goes. So, yeah, sine theta was 4/5, and this thing was from up here, and the coefficient of friction was a half. Look, it's all unfolding before our eyes, guys. Now, the m's are going to mercifully cancel out. Ha! That's very good for us. That always happens. Always happens if you're not considering external pushes or pulls or things like that. Just a body in free motion on in any situation, even if you jump out a window or something. Please don't do that. No matter what your mass is, you will accelerate with the same acceleration due to gravity out the window, and the same sort of scenario happens here. Wouldn't matter what the mass of this thing was, the acceleration will be the same, up or down the plane, in the absence of external pushes or pulls, okay? Now, righty-ho, so what do we get here? Minus 4g over 5, that's right, minus 3g over 10, that's right, equals a. Okay, this is very good. We just have to get this under a common thingamy-bob. There it is. Okay, so minus 11g over 10 metres per second squared. How marvellous. But that's not the end. That's not the end. That's just A. So now we're going to use our license to drive formulas now to work out what V was at the start. Okay, V squared equals U squared plus 2AX, being careful to get this right. Constant acceleration, there you go. Now, this is the formula. Now, of course, in our situation, the initial velocity was capital V. The final velocity is nothing because it comes to rest, doesn't it? That's the point at which it comes to rest. And we're trying to work, no, we know this. We know A and we know X because it went for 6 metres before it stopped, didn't it? Did they say that? Yes, they did, here up here. See? 6 metres. So, therefore, we can work out this little beastie, right? Putting it in, all in the formula. Look, isn't it marvellous? Now, we just do a bit of manipulation, P and thimbles on that, and we get that. Okay, now, if we take the square root of that, we have to take the positive square root because obviously you can't take the negative because V was going up the plane when it was launched up the plane, right? And we chose the positive direction as being this away up the plane. So there you go, that's it. That was the initial velocity up the plane. Do you like it? I think it's mighty fine. Yes, it has to be positive. So that comes to be, if you want to work it out in decimals, on an exam they would say express your answer to 2 decimal places. Otherwise you would leave it like this, exact. You wouldn't fiddle with it unless they asked you, okay? Alright, that was the initial velocity up the plane. Now we've got to deal with B now. This is the other situation where the particle now moves down the plane under its own steam, and we've got to work out the speed of the particle when it returns to where its starting point was at the start of the launch here in part A, okay? So it'll be a different scenario because the forces will be different, guys. We better go over the page and do this. Now, here we go. Now, there's the situation. It's going down the plane now. But see, look, you've got this mg sine theta is the same as before. That's the component of the gravity moving down the plane, resolved parallel to the plane. We've got the mg cos theta the same as before, but this guy here, this frictional force now, it resists the motion down the plane, so it acts up the plane, whereas in the other scenario of part A, of course it was resisting the motion up the plane, so it acted downwards, right? So this is a very different scenario. I'm also going to assume that positive direction of motion for this scenario is down the plane, because that's the direction of motion, and of course mu is a half again. Now, we just have to go through the whole scenario all over again to work out the final velocity when it gets back down to that point there, okay? Alright, let's go. When the particle moves down the plane, it has a different net force. Yes, we know that, Mr. Computer. We were just explaining it, but thanks anyway. N is the same as when it was moving up the plane, so we don't have to rework that out, okay? It was exactly the same. Wasn't it 3 mg over 5 or something? I think that's right. And then let down the plane be the positive direction, yes? So therefore we're saying that the sum of the forces parallel to the plane equals ma. And there we are, okay? So we're going down, so we're saying this one is the bigger force because it's moving down the plane. So this one minus this one must be equal to ma down the plane, right? So there we go. So mg 4 over 5, that's right, minus a half, that one, yes, that was right, I had that right. That's that thing there, okay, mu here, n there, and n was the same as before, equals ma, and therefore we can work out a. The m's are all going to blissfully cancel out again, as I was explaining, and we get that, and we're nearly there, So it looks like a is g over 2, guys, g over 2, right? Now, for the constant acceleration down the plane, now we're going to use the same formulas. V squared equals u squared plus 2ax, and there it is. Now, this time we don't know what the final velocity is. The initial velocity was 0 because it was at rest when it started. A is g over 2, and x is 6, alright? X is 6. So just plug and play, hooray today, yay, and get this, and get that, 6g. That's v squared is 6g, so therefore v is going to be the positive square root of 6g, and therefore, yes, because it's moving down the plane. 7.67 metres per second, there you are. So it was launched with 11 point something or other at the start in part A, and now it finally reaches its destination with 7.67 meters per second because of all the friction. Basically working against it. Basically, that's how it works. So there you are. That was a very interesting question, don't you agree? It's all just a matter of putting diagrams in, draw diagrams in, do the force balances, keep your head, know what you're doing, and get familiar so that your working memory is just cruising along through these questions and you'll absolutely smash them, okay? So there you are. I hope you had a good time. I had a great time explaining them to you. You're a star, and huzzah, you'll go far if you do plenty of practice. All the best, have a wonderful day, and we'll see you next time.